So we'll talk about recursion and we'll talk about introduction to algorithm analysis. And that's, in the simplest forms, how do computer scientists categorize algorithms using time and inputs to measure the algorithm, meaning like, is this algorithm a good algorithm to solve, for example, this sort or this search, right? So that's what we'll talk about. Okay, so let me share my screen here. Okay, so a recursion, right? That's function that calls itself. So if a function calls itself, then in essence it's a looping structure, but it doesn't work like our loops, right? So this is a function calling itself, and just like loops, we have to be careful to make sure that the calling of itself eventually stops. So that is, we need to provide a base case, like we need to provide a condition within the function that tells the function, okay, the condition has been met, stop calling yourself. And then at that time, the function calls start unwinding from the stack. Because if you recall from lectures, anytime a function is called, it's loaded onto the stack. So if the function keeps on calling itself, then it'll be loaded onto the stack. And I've told you from the beginning of the semester that the stack has limited memory. So if a function calls itself a lot of times, eventually, like, it'll be loaded so many times onto the stack and will exhaust the stack memory, and our program will stop executing, meaning it will crash, right? So let's see, I'm trying to cram 2 lectures into one, right? So I have some pre-written diagrams that I'll just explain, right? So this is what I was talking about right now. If we have a function that calls itself and it doesn't have a way of knowing that it's reached its limit or its base case, it loads itself, calls itself, calls itself, calls itself, and notice it's loaded. Each function call is loaded onto the stack n number of times. Eventually we exhaust stack memory, which will cause our program to crash. Okay, so we'll demonstrate this. Like, our program will just stop executing, and then we'll be like, oh, I guess that's it, right? So our program would have to be restarted. So let me see here. I've unlocked module 13 in the examples, and go here into the recursion folder, and I'll start with display. I know it says there 1 in parameter, but for now I am not doing that. I'll come back to it. Remove the semicolon. So okay, so we want to say hello, and then we'll also say load to stack, and it calls itself. So then we say display, right? So the function calling itself, so it's calling itself. And notice here we do not have a condition that meets the base case criteria, so this function will just keep on calling itself and displaying hello and load to stack, just to show that each function calls loaded to the stack. Eventually, after about a minute of executing, it'll just stop executing. So let me go ahead and get this started. Okay, so let me do this. I would have to call it in main, otherwise nothing will happen, right? So main is loaded onto the stack, and then display will be loaded a lot of times afterward. Let's see what happens here. Run. So while this is running, I did post some updated office hours for this week. I'll be available at 8, at noon, and at 4:30, right? So if you're having issues, then it's from now through Friday, right? So you have multiple chances to come by the office hour. Hopefully I can answer any questions you may have, right? So as you can see, like our program's executing, we can see it flickering down here, right? So program's executing, and what's going on right now? Well, a lot of function calls are being loaded onto the stack, and they'll be loaded onto the stack while the stack has room. Once all those addresses are taken, then our program will eventually crash because we've used up all our stack memory. So it's still running, and while it's running, I'll come back to the structure of a recursive function, right? So it's saying that it calls itself, but we need a base case. I purposely didn't put one, so then we will run into this scenario where we crash our program. So what can we do to prevent that from happening? Well, we can provide a base case, right? And then again, pre-written diagram just to save time. This is what we want. We want to have a parameter. Say we want to display 3 times. And within the function, we need to determine what the base case is. So here we'll start counting backwards, right? We didn't have to do that, but usually, like when you want to display something, you say, well, I want to display it n times. So that's why we count backwards. So in the function, we'll say that the base case is 0, meaning if the parameter is 0, then return. If it's not 0, then call the function again, but subtract 1. You see here, like we call with 3 and then with 2 and then with 1, meaning we're always subtracting 1 from the parameter so that eventually we reach our base case and we don't crash our program, right? So let's see what's going on here. So notice our program stopped executing, and I'm pretty sure you've noticed in the homeworks, right? Like when your program just like it stops working and you're like, wait a minute, nothing happened. So that's what happened right here. Like we didn't get a dialogue, but that's fine. Like our program stopped executing, meaning it crashed, and we've actually exhausted all the stack memory. That's not what we want. I purposely created this example just to show you that the stack is limited and that our program will crash once we use all the addresses that are allocated to us on the stack. But this is what we really want. We want to add a base case. We want to add a parameter that helps us track how many times we've displayed hello to screen, and that working with the base case will prevent it from going into an infinite load onto the stack. Well, not infinite, right? Finite, because eventually we crash, and then our program won't crash anymore. So we go back to our source code here. We go and we add a parameter. So we say parameter num, and we have to fix that here too. Parameter num, and then we start with our base case. Or not start, we add the base case. We can say if num equals 0, we've reached our base case. We want to return. Every single function that's loaded onto the stack will execute this code, right? So if we come back and look at df3, so df3 is called from main. Is 3 0? No. So then we load onto the stack, right? But what do we load onto the stack? Num minus 1. Why num minus 1? Because initially we'll call from main df3, but then within the function we have to have a way of decrementing the value of the function argument so that each time we test it with the base case and eventually we hit the base case, which is 0, and then our program will stop executing, right? So if we track it with 3, so d of 3 or display of 3, is 3 0? No. Okay, call the function again with 3 minus 1, so then d of 2, and then it's loaded onto the stack. Is 2, 0? No. So then we call the function again with 2 minus 1, which is d of 1, and then we call it again. Is 1, 0? No. So then we call it one more time with 1 minus 0, meaning d of 0. Is 0 or is num equals 0? Yes, it is 0. And then we come and look at the case, then it's like, okay, start returning. So then our function starts returning, meaning it's removed from the stack, and then d1 executes, right? So d1, all of them were here, like we're paused here because we called the function and we were just waiting. So then when it resumes execution, then we can say, okay, so maybe now can I say hello, unload from stack, so that we can see that this scenario is occurring, right? So then we should see load to stack, load to stack, load to stack, load to stack, and then when it gets the base case, maybe we should also say, well, maybe about we print base case here, and base case will be displayed here, well, not here, right, when it starts returning, and then hello unload from stack will display how many times? 1, 2, 3, right? So let's see if that's the case. So we come back here, we have to go to main, we need to call it with 3. What I'll do is also I'll say cout load from main, or load to stack, it doesn't matter, and then unload. I don't think IOStream is in the header, so I'll have to add it here. Okay, and that should be okay. That should resolve. Yep. Okay, so let's see this in action, right? So now we run it again, running terminal. So notice we load from main, we load display of 3, and then load to stack 1, 2, 3, right? 3, 2, 1, 0, which is the base case, right? What is 3, 2, 1? The parameter, right? So each time we are in there, if it's not, oops, let me come here. If it's not 0, then we call the function again with parameter minus 1. So that's why we say 3, 2, 1, right? So 3, 2, 1, 0. Is num 0? Yes. Display base case. Okay, so notice if we go and look at the output here, we display the base case, and then all the functions call themselves again. So this statement for every function was pending execution. Once we start returning, then notice hello, unload from stack, unload from stack, unload from stack, and unload finally, not from main but from stack, right? So actually that should be just load, right? Not from main, because main is not memory management. So, and that's just the basic structure of how recursion works, right? I mean, as you were just displaying, but we get the structure. Like the function calls itself. We have a base case, meaning like it won't call itself infinitely, and we need a way to make that base case come true. Kind of like the while loop, right? Or the do. Like we need a way to always make sure that when we want to stop, the condition changes to make sure that we can stop the iteration, or in this case, stop the functions calling themselves. So, okay, so I will work on one more example, and we will work on the recursive factorial, mainly because the factorial lends itself very well to showing how a recursion works. So we come here and I'll say, okay, so write prototype int value int return factorial, one parameter num. Okay, we come here, Okay, so the base case. So we can start with the base case, and the base case will be if num is 0, then we know that the factorial of 0 is 1, so we say return 1. And we'll also go ahead and display that we reached the base case. That's the easiest part. We will also create 2 variables, and they are not required. Like if you go and seek the factorial solution online, the code I write, it's like a lot, but it's mainly just to show students like what's happening in each recursive call. We'll have f track return value for factorial, and then we have r, which tracks recursive function call return value. And when we write the code, then you'll see what I mean, right? So if it's not the base case, we need to do something. First thing we'll do is we'll say load stack. What are we going to load into the stack? Num. Okay, so we'll say, okay, maybe I'll change this to n, because I think the example I drew up in the diagram has n, so that way we don't get confused. So n. Okay, so we display n and new line. Actually, n minus 1. And then we say r equals, call the function factorial with n minus 1. Again, it's important to understand that this n minus 1 does not affect the value of n. We are not saving it to anything. This is just for display purposes, okay? And when we come here, then it affects the function argument, right? So then we'll always be decrementing by 1, which is what we want. So notice r will track the return value of the function, okay? And I do this mainly just so that I can show you the math that's going on in each function call, okay? And then we can say f equals n times r. And cout unload from stack. And we want to display n r, and the result, which will be f, so that we can see the math that's going on in each iteration, okay? And then finally, the final return value domain will be f, right? So that should be the value of whatever factorial we decide to feed in here. So let me see here. This one I will write the diagram from scratch because it's a little bit more involved, okay? So we have, say we have factorial. From main we call factorial of 5. And assuming this is main and we have all the correct includes, okay? We have this stack. Function calls here, and we are tracking n, which will be the parameter n. We are tracking r, which will be each recursive call's return value, and at the end f, right? Or actually in each call f. So okay, we'll do that. Okay, so if we call the function with f of 5, then we say, okay, f of 5. So n is 5. Is 5 0? No. So we've not reached the base case. So then load to the stack will be displayed, and then we will call the factorial again with 5 minus 1. So then we say f of 4. And this guy is waiting because we just called the function, but the function will not execute until we reach the base case. So R will not have anything, okay? So then we just say f of 4. Is 4 0? No, right? Why am I saying that? Because we're testing the base case. So is n 0? No, 4 is not 0. So then we need to load the stack again with 4 minus 1. So then we call the function with f of 3. Also, not to lose track that somewhere up here would be more stack memory where main is loaded, right? But I didn't want to bog down the diagram with that, right? So main stack memory would be like up above there, but we're not concerned about that. Okay, is n, which is 3, equals 0? No. So then call the function again with f of 3 minus 1, that is f of 2. Is 2 0? No. So call the function again with 2 minus 1, meaning f of 1. And finally, is 1 equals 0? No. So then call the function again with n minus 1 or 1 minus 1, which is 0. So then f of 0. Okay. So we are here. N is 0. Is n 0? Yes. Display base case. Return 1. Okay. So return 1. We're tracking R there. So return 1. So we return 1. So factorial returns 1, meaning R is 1. So then we need to multiply n times R, right? So okay, so let's do that. N times R. So let me get a different color. N, right? Times R. So multiply those. 1 times 1. 1. Okay, so then we come back over here. So we're saying n times R. So 1 times 1. 1. Okay, so then we return f, which is 1. So then this function is pending execution. So then we're like, okay, so we know we need to get the value of R from factorial. And if we look at this, then the return value is 1. So then we're like, okay, so we need to do 1 times n. Okay, so what is the value of n? Oh, sorry. This n. So multiply them. 2 times 1. 2, actually, I should put this one over here, right? Because that's f. So then 2 times 1, 2. Okay. So then I come back over here. 2 times 1. So that will be 2. And then I can make that my return value. So then I say, okay, 2. And then multiply what? It's always the same thing, right? N times R. 2 times 3. 6, right? So then I come back over here. So I return 6, which is saved into R. So now I do 6 times n, and I come back and look at this. So save it to R, and then 6 times n, which is 4. So 4 times 6 is 24. Let me erase this. I'll do that. Okay. So 24, actually 24 over here, right? So now I need to do 24 times n, so f goes into r, so 24 times n, which is this one, so 24 times 5 is 120, which is the factorial of 5. So if we run this program, we should see that answer, right? And more importantly, the math that I was showing you here in the diagram, we should see it in the output too, mainly because I've added extra code to make sure that students are able to see that, oh yeah, the functions are loaded onto the stack, it's pending, and eventually once it reaches the base case, they start unloading, and then this execution takes place afterward, okay, including the value of r. So let's go ahead and run this program. Run in terminal. And we come up here. Right, so load the stack, right? I should have put here like load with f of 5, right? But I didn't. But you can see here that that's what we load, okay? This one right here, load f of 5, and then load with 4, load with 3, load with 2, load with 1. Base case is reached. The base case we display. We start returning, and notice the multiplication that I was showing you all is displayed for us, right? Where we do like 1 times 1, 2 times 1, 2 times 3, 6 times 4, and finally 24 times 5 to show that that is the factorial of 5. And if you do this with a loop, you'll get the same answer, right? So this was an assignment during the semester where you had to use a loop to do it, but now we do the same problem, but we solve it recursively, and that's how you would use recursion to solve a big problem, right? Which we know recursion is factorial is 1 times 2 times 3 times 4 times 5. So we did that with repetitive function calls, right? So let me come here. So are there any questions? The quicksort, they in data structures, they use this probably around the 5th or 6th week in data structures. So and the introduction to algorithms, which is the next topic, like I'm pretty sure they'll be introducing it as the semester progresses, right? So I guess there's no questions here. Will I see questions about this on the exam? Yes, you will see questions about this in the exam. You will not get a problem that asks you to solve a recursive programming problem, but you'll get questions about the structure of recursion. You may get a question that shows you code like this, and then it'll ask you to choose from the multiple choice what output you'll see. Okay, so that's the kind of questions you'll see. Like you'll get questions that'll ask you like how do you keep a recursive problem from recursively calling itself, right? And that will be, well, you need a base case, right? So you'll get questions like that. Okay, so right now it's 6. You should see an attendance quiz pop up, and all you have to do is submit it. Okay, you don't have to answer any questions. You just have to submit it, and then it should be up right now. Afterward, I'll continue with the next topic. What's today? The 10th? Yeah, I see it there.